Hello, and thank you for joining me in this lesson. Today, we will explore annuities. So, whenever we say the word annuity, we have to think of a regular payment. A regular payment can be made towards the future when we are saving up money, or regular payment can be made to pay off a debt or to generate income from a certain amount of money that you either owe or own. These two words are so close to each other. So, our focus today will be on what we call the present value of an ordinary annuity. And to understand what present value of an ordinary annuity is, I brought in two examples. So, here is the story of your life. Imagine you won a lottery, $6 million going straight to your bank account. You don't want to spend all the money in one day, right? So, you decide to sit down and calculate how to manage the money you won in order to generate regular amounts over equal periods of time up to a certain age. So, you're smart and you want to be rich every day. So, your $6 million is called present value. It is money you own and where you can generate regular payments. Here is another life story. You decide to buy a brand new car and you'd like to finance it with zero down payments. Your brand new car costs $35,000, and this means that you will be in debt $35,000 and start paying off the car in regular payments. The $35,000 is what we call the present value from where the financial institution will generate regular payments from you. So, in both these situations, in order to solve the problem, we use a formula that we call the present value of an ordinary annuity formula. So, this is what it looks like. PV, which stands for present value, equals, we build a big long fraction, and we start off with R. And you've guessed it, probably already guessed it, that R stands for regular payments. And then we're going to close the square bracket somewhere here. We have round brackets, we have minus. So we start off with 1 minus, and I bet you've seen this very often. So 1 plus I to the power of n. Now, there is something different in this formula when we discuss present value. Remember that in present value, you own the money and you are paying the money that you are generating income from the money you own, right? So you're not saving for the future. So in a way, we're kind of going back in time. And this is even clearer when you think of you owe money to a financial institution and you are paying off your debt, the money you own. So you're kind of going back in time because you're not saving for the future. You're using from the past. So this is the reason why N will have a negative sign. And it is very often overlooked and easy to forget. Please don't. And then we divide by I. So now let's talk about all these letters. So what is the meaning of them? So PV stands for what we call the present value. The present value can be either money that you own and you generate regular income from, or the money that you owe and you are paying it off, right? In regular payments. So R stands for regular payments. Now, the letter I stands for interest rate per compounding period. Remember that in any financial institution, when we apply for either a savings account or when you are applying for a loan, the bank will give you what is called the annual rate. Now, the annual rate is the interest rate in percentage that you will have to pay for 1 year, and it is indicated by letter R. Now, the annual rate R is spread over the compounding frequency. For example, if money compounds monthly, then you will have to find the interest rate per every month. We call it per every compounding period. So if money compounds monthly, that means that in 1 year, there will be 12 compounding periods because there is 12 months in a year and every month represents one compounding period. And the interest rate per compounding period would be equal to the annual rate divided by 12. So the annual rate is spread over the 12 months equally. Now, as we have explained in class in the previous lessons, if the money compounds quarterly, which means 4 times a year, then that means that the annual rate will be divided by 4 because it will be spread over the 4 compounding periods equally. Now, N stands for what we call the number of compounding periods. Now, the value of N depends on 2 things, the time and compounding frequency. For example, if you make the payments or if you're paying off a loan for a certain number of years, T stands for time in years, at a certain frequency, for example, in our case, monthly. That's just an example because the compounding frequency can be different based on the terms and conditions of your savings or your loan. It means that, for example, over a period of 10 years, if you are paying monthly, you will have to pay eventually 120 regular payments, or you have to make 120 regular payments. So N stands for the number of compounding periods, the total number of compounding periods, or the total number of payments. So you can look at it either way. So I brought in an example for us to discuss so that we can use this formula and better understand how to solve such problems and how to use this formula in the meantime to solve our problems. So here is Luke's story. So everyone in the neighborhood knows Luke. He's very hardworking and smart. But what people love most about him is that he's very kind. So Luke started post-secondary 4 years ago, and before he was even finished with his studies, he was able to find a job. So I told you he's smart. His supervisors loved Luke, and he was able to move up the salary ladder pretty fast. Did I mention that Luke is very hardworking? So Luke was very happy with his work, but his secret dream was to build a business of his own. And so he did. His business grew very fast. Luke loved talking to people and helping them solve their problems. So yes, kindness does take you far in life. So a day had come when Luke decided to buy his very own dream house. He starts hunting for one and lays his eyes on a property that cost $850,000. He puts on his best suit and best attitude, heads out to the bank where he meets with a mortgage specialist. He agrees on the following terms. Luke will be able to make a down payment of 20% of the price of the house. In this way, he can avoid paying CHMC. So this is the insurance you pay for the mortgage itself, or just for the fact that you owe money to the bank. You will have to arrange a mortgage for he will have to arrange a mortgage for the rest of the amount based on the following terms. So 20-year amortization, which means he will pay the mortgage over a period of 20 years, with payments made monthly at the annual interest rate of 3.9%. So these are the rates nowadays. And the money will be compounded monthly. So we'll have a few questions to answer so we can help Luke figure out what the payments are going to be and how everything will roll out. So first we have to determine Luke's down payment. Now remember that Luke is paying 20% down of the price of $850,000. Now remember that 20% means 20 divided by 100. Of means multiplication, right? So multiplied by $850,000. So 20% or 0.2 times $850,000. Let's see how much he's able to put down for his house. I'm going to use my calculator here. That's just for speed. I like to use the calculator on my iPad too, but going back and forth can take a little bit of time. So it seems that Luke is paying $170,000. So he saved up quite a bit of money. Now, because he's putting down this amount of money, it means that he won't have to borrow $850,000. So the principal mortgage loan would be $850,000. Take away $170,000. And this would equal $680,000. So Luke will have to arrange for a mortgage of $680,000. And now he's thinking, with the terms and conditions, which, let's recall again, the annual rate was 3.9%, compounded monthly. The amortization was over 20 years, again monthly. We need to know what the regular payments will be. We know that the amount of mortgage or the loan, the mortgage, the present value, we can say, the money that he owes is $680,000. So this is a present value question because this is amount of money that you've borrowed and the financial institution, the bank, will make or will withdraw regular payments from you. So for this, we're going to have to use the formula PV equals. I'll rewrite the formula one more time. I know it's an extra step, but it assures higher accuracy in problem solving. And it's nice to kind of get acquainted with the variables that you are working with. Okay. And now we are going to substitute everything. And before I do so, I like to calculate the values of I and N before I plug them into the formula here. So I want to do that separately. So I will say that the interest rate per one compounding period would be equal to, remember, monthly means that the frequency is 12 times a year. So that would be the interest rate R, which is 0.039 in decimal form, divided by 12. Okay, so divide by 12 because monthly. Now, the time in 20 years, every month making a payment, which means 12 payments a year, will guarantee a number of payments 20 times 12. So we're multiplying by 12 because, again, the frequency is 12 times a year. So the total number of payments will be 20 times 12, or 240 payments. So all we have to do now is substitute the numbers in. The present value is known to be 680,000. Count the zeros, everyone. Here we go. And then we have a regular payment which is unknown to us. 1 minus 1 plus 0.039 divided by 12 to the power of negative 240. Don't forget the negative. It's very easy to overlook at the negative here at the very end of the formula. Over 0.039 divided by 12. So now we have to calculate. And what I like to do usually is focus only on this part of the formula. So this number. So when you use the calculator, please try to type the expression in just like it appears in here, which means that you're going to start with brackets. And then you're going to press 1. and then minus. And then you will open brackets again, and then 1, and then plus, and then 0.039 divide by 12. You go to close the brackets, press the power button. It can be either as a hat or YX, depending on the calculator. And don't forget that this is the negative sign, not the subtraction in the calculator. And then press 240. Now you got to close the brackets. So that's the bracket you open in here, you got to close in here, right? And then divide. Now remember, when you divide by a fraction, you got to keep this fraction in the brackets, inside brackets. The reason why is because of bad math. If we don't, then the calculator will do something weird. So it will recognize bad math. It will divide by this and then divide the whole expression by 12. So which is going to actually distort our answer. So 0.039 divide by 12, and I will close the brackets again. And now the exciting part, I will press equal sign. So when I press the equal sign in my calculator, I saw that I had number 166.4657. And you know what, you can round to 1 or 2 decimal places in here. It doesn't really matter. What I prefer to do is keep the number in the calculator. And I know that to isolate R, I will have to divide both sides by 166.4657. But when I perform the division, 6 by 7 here. So when I perform this division though, I start off by typing up 680,000 and then divide. And instead of typing this number, you can press a button in your calculator that says answer. Okay, so every calculator has this button or this function. So try to find it because it's hidden in different spots in every calculator. If not, just typing the number as is. I will divide by the answer, and I got $4,084. So the regular payment is $4,084.92 actually. So this will be what Luke has to pay every month. I'll make this a little prettier. So this is the regular payment he will have to make every month so that he be able to pay off his mortgage in 20 years. Now, the next question is asking, what's the total amount that Luke pays over the life of the mortgage? Well, think about it. So he will be paying every month this amount. So we'll say that in total, he will pay $4,084.92. How many times? Well, as many regular payments, many as the number of the regular payments. So 240 times, which means that we have to multiply by 240. So I still have my answer in the calculator, so unround it, so the precise answer, and I will multiply it by 450. So what I got in here was, or is, a ridiculously big number. And I'm gonna, no, one second. So it's 4,084.92 times 240. Okay, so what I got in here is 980,000 and $380.80 at the end. Okay, so this is the total amount that Luke will pay eventually, right, once he's done. Now, when you think about it, this is the amount of money that he borrowed, right? That was his loan right here. And this is what he ends up paying at the end. So do you think that Luke is paying the exact same amount as he borrowed? You would say, yeah, sure, and some more. Now, why is he paying more money? What is that for? Obviously, that's the interest that has gone towards the bank profit, right? So the total amount that Luke pays over the life of the mortgage is greater. And obviously, that is because he's also paying for the interest. So the interest paid is the difference between what he borrowed and what he paid at the end. So what he paid at the end is $980,380.80, and what he borrowed was $680,000. So he is paying an interest of $300,000, right? And 380 cents. So that's the interest he pays. So I hope that this helps you understand how loans and mortgages work in general. And I hope this made sense. Thank you for watching.